welcome back to Calculus. Today we're going to be looking at section 4.3, monotonic functions and first derivative test. All a monotonic function is it's a function that either only goes up, only goes down, or I guess it could just stay constant. That would be monotonic as well. So it's not going up and down. And we're going to look at these in terms of not maybe the entire function, but on pieces of the function. Where is it going up? Where is it going down? So we have this corollary. It says, suppose f is continuous on the closed interval AB and differentiable on the open interval AB. Then we get a couple of things out of that. If f prime of x is greater than 0 for all x in open interval AB, then f is increasing on closed interval AB. And if f prime of x is less than 0 for all x in the open interval AB, then f is decreasing on the closed interval AB. Now, one really important thing to consider here. I think this makes sense. First of all, the derivative being, well, let's just consider the increasing case. If the derivative is positive everywhere in this interval, well, what does that mean? A derivative is like the slope of a tangent line for any point, for all those points in that interval. And if all of those slopes are positive, I think that seems reasonable that the function itself is increasing on that interval. But here's the kicker. That does not mean that the function is positive. Okay? A positive derivative just means the function is going up. It's very easy to draw a function that is going up on an interval, but has negative values. So please don't confuse those two things. Sometimes that happens. All this means is that the original function is going up or going down. It does not say anything about whether the original function is positive or negative. All right, so let's move into the next board and start using this. All right, so here's our first example. We're going to figure out intervals of increasing and decreasing. So it says find the critical points of f of x equal to x cubed minus 48x plus 13 and identify intervals on which f is increasing and decreasing. So you can see here I started by finding the derivative. So f prime of x is 3x squared minus 48. Again, drop the exponent down, and this x is going to disappear, and so is the 13, right? It's a constant, it goes away. So then I chose to go about doing this by factoring. We set it equal to 0, and I factored it. The 3 comes out, it's a difference of squares, and I get -4 and +4. You could have thrown in the quadratic formula. I guess technically we could have added 48 to both sides and solved by taking a square root. But anyway, I get 4 and -4. So what I do then is, since these are my critical points, think about what we have graphically. Critical points are going to be the top or the bottom of hills on a graph. And so those are going to be the places where your function could switch from being increasing to decreasing. Now, there's no guarantee that it switches at those points, but those are the places where it could switch, right? It's going to be really hard to go from increasing to decreasing without passing through a point where that tangent is 0. So I like to think of this in terms of a number line. Here's the two places where my function can change. And at this point, you can just pick numbers in these intervals. You can also check the signs of the pieces if you want, but you can just plug in, say, -5, 0, and +5. And here we're going to plug those into the derivative because we want to know, is the derivative positive or negative? And since these are the only places where that derivative can change signs, all we have to do is test the intervals. So you can see I came up with that out to the left here, the derivative is greater than 0. In between, it's less than 0. And out to the right, it's greater than 0 again. And so from that, I can say that the function is the original function, f of x, is increasing on the intervals from -infinity to -4, and also from 4 to infinity, and then decreasing on that middle piece from -4 to +4. There we go. That's it. Increasing and decreasing. So from this, though, we're going to be able to go ahead and get one more thing out of it. It's going to be called, let me look, just so I get it right, the first derivative test for local extrema. So I'll have that on the next board, but basically, well, it works two ways. We use these critical points to identify where our function is increasing and decreasing, and we're going to go the other way. We're going to be able to say, hey, it goes from, in this case, increasing to decreasing. That means this one's going to end up having to be a maximum value. So it'll be some sort of local or absolute maximum here at -4. And this one would go from decreasing to increasing, which again, if it goes from down to up, means you're going to get a minimum value. So we'll look at that on the next board. Okay, so here's our first derivative test. I've kind of abbreviated it just a little bit, so go back and look in the book and see the full extended version with all the conditions and criteria. Mostly it just needs to be continuous and differentiable everywhere except possibly at the critical point C. Alright, so the first derivative test, we're going to use C as a critical point, and then we get three things. If f prime changes from negative to positive at x equals c, then f has a local minimum at x equals c. And again, I think that makes sense. If your original function is coming down, right, that's what it means for the derivative to be negative, it has those negative slopes, and then it goes to going up, you get a local min. If it does the other way around, if it changes from positive to negative at x equals c, then f has a local max at x equals c. And then finally, if f prime does not change sign at x equals c, then f has no extrema at x equals c. And I just gave a real quick example here to show us one where there's no extrema. Y equals x cubed. So it's this lovely graph that hopefully we're all quite familiar with. And if you took its derivative, you'd get y equals x squared. Its critical point would be at 0, right? The x squared is equal to 0 at 0. But that's definitely not a max or a min, right? It comes up, it hits that point, and it keeps going up. And that makes sense because if you take the derivative, x squared is positive everywhere except at that critical point of 0, where it's 0. So the derivative never switches signs. It's always positive, meaning no critical point. All right, so let's do an example of putting the first derivative test to use. Okay, so here's my first example. I want to find critical points, intervals of increasing and decreasing, and any local extrema for this function g of x is equal to negative 3t squared plus 9t plus 5. So the good news is all the parts of this question, critical points, the intervals, and extrema are all connected together. Right, that's what we get out of that first derivative test. So I take the derivative, drop the 2 down, we get negative 6t plus 9, and the 5 goes away. I set it equal to 0, and when I solve that, I get 3 halves. Okay, 1.5 if you prefer. It is a nice decimal, so you could use that. And so then I come over here, and now I start examining what I have. So I make my number line because I just really like the graphical representation of it. There's 3 halves, and then I plug some numbers in to the derivative. Make sure you plug them in here to the derivative. So let's say we plugged in 0 to the derivative. Negative 6 times 0 would be 0 plus 9 would be positive, so we get that the derivative is greater than 0. And out to the right, maybe we plug in 2. Negative 6 times 2 would be negative 12, and 9 is negative 3, so that would be negative. So anyway, you can just test points in these intervals. What that tells me is that 3 halves is a local max because it goes from increasing to decreasing. Right? It goes up, and then it comes down. So I plug in 3 halves, which gives me to the original function, and that gives me the maximum value of 11.75. So you can see I wrote down we had the max at x equals 3 halves with a value of 11.75. And then I also then needed to identify the intervals of increasing and decreasing, and I just pulled those right off of my number line up top. Increasing from negative infinity to 3 halves, and decreasing from 3 halves to infinity. So there you go. I've got one more example, and we'll see what happens with it. Okay, so here's my next example. F of x is equal to x cubed over 3x squared plus 1. To take this derivative, I'm going to need to use the quotient rule. So I started by calling the top u and the bottom v, just like in the rule that we had. That's called the quotient rule. And I took those little derivatives. Derivative of the top is 3x squared and the bottom is 6x. And then I pieced together the derivative using the quotient rule. So you can see I have the bottom piece times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And I'm going to leave you guys to do this, but if you multiply this out and then do a little bit of factoring, you can turn this into 3x squared times x squared plus 1. All over 3x squared plus 1 squared. And there's a good reason why we want it to look like this. That is because now we have to set it equal to 0. Okay, and so it's going to be much easier to work with when all we have are pieces that are multiplied and divided. Because what gets you 0? If just one of those pieces is 0, you're going to get a critical point. You're either going to get a derivative of 0, or I suppose if the denominator here was 0, you get an undefined point for x there for the derivative, but that's also a critical point. So, turns out the only way to get 0 here is if x is 0. I'm just going to kind of wave my hands at this. I didn't put it on the board, but basically 3x squared is 0 when x is 0. X squared plus 1 is always positive. Okay, if you don't believe me, think about that one just a little bit. I think you'll be okay. And 3x squared plus 1 is also always positive. So since neither one of those two pieces can be 0, the 3x squared is the only thing that gives us our 0, and it's at 0. So here's my number line with a 0 on it. So then what you want to do, again, go back, you can test these intervals. Maybe use -1 and +1. Okay, if you do that, what you're going to find is that this is always positive, except at 0, where it's 0. On the left-hand side, it's greater than 0. On the right-hand side, it's greater than 0, which means we have no extrema, right? That's that third part of the first derivative test. But we can say that the function is increasing from -infinity to 0 and from 0 to infinity. Technically, it's not, actually no technically, it's not increasing at 0. It is flat right at 0, right? This function comes up, it levels off for just that instant at 0 and then goes up again. So you don't get to say it's increasing on the whole function, just everywhere except 0. So there we go. That is the first derivative test. Have fun putting it to use, and I'll see you in the next video.